your entertainment. So I'll be writing it with solutions, but I haven't written solutions yet. I'll just be doing solutions and then after the remaining time we have. I have to leave actually a little early, but okay. LMR. These are basically what I did in class. Should I do these? I just made, okay, so we have, let's say that R is equal to S. And should I do these ones? I mean, actually I did these in class, but should I do this LR? Sure. Okay, let's do this. A. So what you do for the log likelihood ratio, you first compute you just write P of R given C equals 1, P of R given C equals 0. Okay, so P of R given S. Alright, this is just an additive channel, so this will just be the density of the noise minus S. This is Gaussian, alright, so this will be 1 over root pi n0, because it's n0 over 2, alright, E. So L of R equals, okay, so if C equals 1 is the same as S equals A. So that's the only little trick. Everything else is pretty straightforward. All right, and the constants cancel out in that probability. So that will be E. Okay, that's just because the exponentials, when you E of A over E of B is E to the A minus B. All right. So the log and the exponential cancel out. I get a minus 1 over n0 r minus a squared. Wait. Oh yeah, okay. I should just do it like this. All right. So there's an r minus r squared and a plus r squared. They cancel out. Then I think there's a, I think it works to be 4ar. Let's say it was a different noise. So basically this log likelihood ratio tells you if R is positive, it's more likely that bit C1 was transmitted. That makes sense, all right? And if R is negative, it's more likely that bit 0 was transmitted, all right? For this. Okay.
Say that again? If R is what?
If R is positive, then it's more likely that bit C equals 1 was transmitted.
Okay.
Because this ratio is, when the numerator is bigger than the denominator, that means this number is bigger than 1, which means that this is positive. When it's less than 0, it's negative, so.
Okay.
All right? Okay. So now let's say that, okay. This is actually called Laplacian noise. All right. Yeah, okay. So it kind of looks like an exponential on both sides, right? So it has this exponential loop there like this. So in this case, it's basically the same idea, all right? So in this case, same thing as before. P of R given S is P sub W. Because it's an additive channel, it's R minus S, right? And in this case, so L of R will be log of Now, this guy here will look like the 1 over 2 lambdas. Oh, wait, so that's log of you just subtract these. So with this guy, I'm just going to substitute down here. Okay. The log next, so it's like, did I make a mistake? R. Okay.
Sandeep?
Yeah.
PR given S equals PW. That's given, right? Yeah, this.
This one's given, yeah.
Okay, so we don't have to know that, like it's given.
No, you have to give it.
No, not that one. The formula down.
This one.
Yes.
Oh, this one you know, you would be able, you should know how to do this.
Okay.
Oh, this is, and because R is equal to S plus W. So once you see this, remember that this is an additive channel. As long as it's like this and W is independent of S, right? All right, so it's an additive channel. So you definitely want to know this equation. So then that if W is independent of S and you have this, P of R given S is just this.
Okay.
So that's R plus A minus R minus A. Okay, so if actually you were to draw this, this will actually kind of look weird. Okay, so if you were to draw this, what would this look like? What does actually R plus A look like? The absolute value of that. So that's 0 when R is equal to minus A, all right? And then it looks like a V, like this, okay? This is absolute value of R plus A. And then if you look at R minus A, it looks like this. Okay? Now, interestingly, what happens is, if I subtract these two equations, all right, then you're going to get when, yeah, so what will happen is, it will look like, it will actually look like this. You can convince yourself of this, I will. When I know I subtract it, it has to be like piecewise linear, it'll look like this. All right. It'll cross at 0, it'll be 0. At R is equal to A, I'll get, this one is 0, I'll have 2A over lambda, all right? And here I'll have minus 2A over lambda. So it kind of looks like the log likelihood function for the Gaussian case, all right, in this regime. But if I start to see very, very high values of R, it becomes no more likely than it was here. So just like in the, remember, just in this case, it was also a linear function. This 2 is a linear function, all right, but it ends up kind of clipping at these two, saturating at these two extremes. All right, the concept is that for small values, or values between like plus or minus a, it's just like a Gaussian. But for very large values, then anyway, it just doesn't get any more likely than this.
How do we know it's kind of like how do we know it's an upside down triangle?
How do I know? It's like, so this one, so you could, okay, how would I know to draw this?
Yeah.
So the way I would draw this is, I know that it has to, because in every region here, it's a sum of 2 lines, all right? So it has to be a linear function. So I just have to get the slope and the intercept at each of these points, and then draw them. So in this region, this will have a slope of -1, and this guy will have also a slope of -1, but I'm taking the negative of that one. So it'll have a slope of 1 and -1. So it'll cancel out and be flat. And then you just keep on working.
Oh, okay.
I mean, whether I'd actually make you go and draw all that